Hello, my name is Cassi Lochhaas, and I'm a postdoc at Space Telescope Science Institute, working with Molly Peeples and Jason Tumlinson as part of the FOGGIE team. Today I want to tell you a little bit about some of the work I'm doing there, as well as some work that I've done in the past at the Flatiron Institute with Greg Bryan and Drummond Fielding and a few others there. What I'm interested in is using simulations to understand the overall structure of the circumgalactic medium. Clearly, we can tell from this video that the CGM is a highly structured and dynamic environment, but it is common for static analytic models to be used to describe it. So what I want to know is how well do these models actually hold up within CGM simulations, and in particular, what models should we actually be using to describe CGM observations and to understand how the CGM influences galaxy formation and evolution as a whole. One model that is very commonly used is the assumption of hydrostatic equilibrium, which says that the gravitational potential of the galaxy and its dark matter halo is exactly opposed by the hot thermal gas pressure of the gas within the halo. Not only can the pressure support of the gas there tell us whether or not the gas is in hydrostatic equilibrium, it also determines the fate of the gas, where gas that is underpressurized relative to gravity may fall in towards the central galaxy to potentially fuel star formation. Gas that is overpressurized relative to gravity may outflow into the IGM, and gas that is exactly in equilibrium, like in the hydrostatic equilibrium assumption, may stay within the CGM for an extended period of time. In order to assess the pressure support of gas within the CGM in realistic simulations, I used Drummond Fielding's 2017 idealized simulations, where the galaxy is not being simulated at all. It is just a black box in the center of the domain, and there is no cosmological evolution. But these simulations can get to very high resolution within the CGM that allows them to track the important dynamics on small scales of the gas there. In particular, there are two different halos that I'm looking at here. There's a low mass 10 to the 11 solar mass halo, and a high mass, roughly Milky Way mass 10 to the 12 solar mass halo. So we want to use these simulations to characterize the overall pressure support of the gas in the CGM. So in order to quantify the pressure support of gas, I define this parameter, alpha sub HSE for hydrostatic equilibrium, that gives the ratio of the thermal pressure to gravity within the simulations. So if this parameter is exactly equal to 1, then the gas is in equilibrium. If it's greater than or less than 1, the gas is overpressurized or underpressurized relative to gravity. It may be either outflowing or inflowing. Looking first at the high mass, roughly Milky Way mass halo, the hot gas is only in pressure equilibrium in the outskirts of the halo and is somewhat underpressurized relative to gravity in the inner regions, whereas the cold gas is underpressurized throughout, which is pretty much what you would expect. The low mass halo is not in pressure equilibrium anywhere within the halo. The hot gas is underpressurized everywhere throughout, as is the cold gas. So you might expect that in the low mass halo, this would indicate that this galaxy is collapsing in on itself, but that's not what we saw in the videos that I was just showing. So instead, what we actually need is other types of gas pressure support than just the thermal pressure. In particular, we can consider turbulent pressure support and also pressure from outflows and inflows in the form of ram pressure. So now we can define a new parameter, alpha sub E. I've dropped the HS because this is no longer a hydrostatic solution because we are including these dynamic pressures, where again we have the outward pressures on the top, which is thermal pressure and both turbulent pressure and outflow ram pressure. And then on the bottom, we again have gravity and now inflow ram pressure that acts in the same direction as gravity. So looking again at the high mass halo first, now we can see that even in the inner regions where before it was underpressurized when considering only thermal pressure, now throughout the entire halo, the gas is in pressure equilibrium, but it's not a hydrostatic equilibrium, it's a dynamic equilibrium because we are now including these dynamic pressure support terms. The low mass halo, however, is still a completely different story. The warm gas is closer to equilibrium, but the cold gas is now drastically overpressurized and is actually outflowing within this low mass halo. So what these idealized simulations have told us is that in the high mass halo, roughly Milky Way mass, the hot gas is in a dynamic, not a hydrostatic equilibrium. But in the low mass halo, there is really not any type of equilibrium at all. Neither the hot nor the cold gas is in dynamic or hydrostatic equilibrium. But these are idealized simulations. We can now bring this same pressure support analysis to a cosmological simulation, which can track how galaxies evolve throughout cosmic time. It can also track spherical asymmetries such as inflow filaments or rotation of the halo gas. These simulations can be a little bit more difficult to decompose to understand the pressure support terms, but they are a little bit more realistic. The cosmological simulations that I'll talk about here are the FOGGIE simulations, figuring out gas and galaxies in ENSO. And these are cosmological zoom-in simulations that place a significant amount of resolution within the CGM. And it's spatial resolution, which means that even the diffuse gas is being resolved to a high degree. So these simulations can allow us to look at the very small scale differences in the pressure support of even just the diffuse gas within the CGM. So if we look at the pressure, the thermal pressure of the gas in one of the FOGGIE halos, with the galaxy disk edge on at the center here, we do see that in general, the thermal pressure is higher close to the central galaxy and decreases the further away you move from that galaxy, which is what you would expect from hydrostatic equilibrium. However, there is still significant small-scale changes in the thermal pressure at any point within the halo that indicates that perhaps there's something a little bit more going on here than just a simple hydrostatic equilibrium. And we can look at our HSE parameter once again, where now we're coming back to only thermal pressure relative to gravity, where if the CGM in this simulation was in perfect hydrostatic equilibrium, this entire image over here would be white. But it is of course not. We can see dark green regions that show overpressurized regions such as the outflow above and below the galactic disk. We can see brown that shows underpressurized regions such as inflow filaments that are poking in at the edges of the box. And also the rest of the halo gas and the volume filling medium has small scale deviations from green to brown, from overpressurized to underpressurized throughout the entire volume. So clearly there's significant structure in this parameter that indicates that not even the diffuse halo gas of the CGM is in perfect hydrostatic equilibrium. So I just mentioned that we can kind of break down the CGM into a few different regions, such as the hot outflows above and below the disk, the cool inflowing filaments poking in from the edges of the box, and the warm halo gas that makes up the rest of the CGM. If we plot our HSE parameter as a function of radius now, we can tell that while there is some of the CGM that is in perfect hydrostatic equilibrium, there is still a huge range in values here. On this plot, each point is one cell within the simulation, and they're color-coded by the temperature of that cell. So if we consider our large-scale structures within the CGM, then we can tell that the hot outflow region is what is mostly overpressurized. The cool inflow filaments are what are mostly underpressurized. But even that volume-filling diffuse halo gas is still not in perfect hydrostatic equilibrium and has a range of values of this HSE parameter. So what we want to understand is what actually drives these deviations from hydrostatic equilibrium, and how does that impact how the galaxy grows and evolves, and how does that impact CGM observations. So this project has been funded with an HST AR theory grant, so keep an eye out for the results coming from this soon. In particular, I want to focus on this halo gas that shows up as this green color here that is not part of either large-scale outflows or large-scale inflows. This halo gas is generally thought to be at the virial temperature of the galactic halo, but this may not necessarily be the case. If we look at a distribution of the gas temperature as a function of radius out to the virial radius in one of the FOGGIE halos, and compare this to the standard virial temperature that we would expect for this halo, we actually find that the gas in the halo is about a factor of 2 colder than you would expect. In order to understand why this might be the case, let's take a look at the derivation of the virial temperature, and also at the same time, let's look at a derivation of a modified virial temperature as well. So first, both of these virial temperatures start with the virial equation, which relates the potential energy of the gas in the halo to the kinetic energy of the gas. In the standard virial temperature derivation, the kinetic energy is given only by the thermal kinetic energy of the gas and nothing else. In our modified virial temperature, let's assume that instead the kinetic energy is given by the sum of thermal and non-thermal kinetic energies of the gas. In both cases, the thermal kinetic energy depends only on the temperature of the gas, and the potential energy is given only by the mass and radius of the dark matter halo. For the standard virial temperature, this gives a temperature that depends only on the mass and radius of the halo, Whereas for the modified virial temperature, the temperature does depend on those as well, but it also depends on this non-thermal kinetic energy term, which we can estimate from the gas velocities within the halo. So if we come back to our plot of temperature as a function of radius, and now we overplot our modified virial temperature, we can see that it does a much better job of describing the bulk of the mass of the gas in the halo's temperature, more so than the standard virial temperature assumption does. So it would appear as though the halo gas is actually not being described well by the virial temperature, and it is instead better described by a modified virial temperature that includes the contribution of non-thermal kinetic energies to the overall energy budget of the halo. And yes, we did check that at this point that we are measuring this, the halo is in fact virialized. So this paper came out very recently on the archive, so take a look if you're interested in a few other results that are related to this, and in particular some of the implications of a 2 times colder CGM than it is normally assumed from the standard virial temperature. Just want to highlight a couple of those implications here. First, if we assume that there's cool gas that is located in pressure balance with the hot gas in the halo, then this pressure balance is actually going to occur at a lower thermal pressure than might be expected. The cooling time of the hot gas is much shorter as well because it's a little bit cooler, and this could lead to even more cool gas production within the halo. Halo gas mass estimates from X-ray surface brightness profiles might not be correct because these estimates usually assume that the hot X-ray emitting gas is extended all the way out to the virial radius. But that does not appear to be the case in that the temperature of the gas gets a lot cooler as you approach the virial radius. And in particular, there's a question of oxygen-6. Oxygen-6 may be tracing a sort of intermediate temperature gas, and it appears that the prevalence of oxygen-6 traces a certain halo mass, which may indicate that it's tracing the virial temperature of gas within that halo mass. However, as McQuinn and Work 2018 pointed out, it doesn't quite work out just right, where the O6 is seen at a slightly higher halo mass than you would expect from a standard virial temperature assumption. Although the modified virial temperature is a little bit cooler than the standard virial temperature, which might shift the place in halo mass where we most expect to see oxygen-6 because the temperatures in these halos are a little bit cooler than would be expected, thus shifting the location where oxygen-6 is seen to slightly higher halo mass. So this could reduce this discrepancy and find that O6 is still tracing the virial temperature, just not at the same temperature that you might expect. So the way forward with all of this is that clearly we need dynamic models for the CGM, not simple hydrostatic models. The dynamic motions of gas within the halo affect not just the pressure support, but also the overall energy budget of the halo, which then impacts the temperature of the gas in the halo as well. And another nice thing about CGM dynamic models is that they can give us some insight into the velocities of the absorption lines that we see in CGM observations so that we can understand those as well. If you found this interesting, please take a look at some of my other work that I did not talk about here, which you can find on my website, or feel free to send me an email. Thanks for watching.